Good evening, everyone. Welcome to the third week on live problem solving session in GATE Metallurgical Engineering. I am Santra Krishnan. These live sessions are brought to you in association with NPTEL and PMRF. So far, in the last 2 weeks, we had been solving previous year GATE Metallurgical Engineering questions. I hope all of you have gone through these questions, and in case you have any doubts, please do feel free to reach out to me. And I would advise that you attend these sessions weekly on Thursday from 6 p.m. to 7 p.m. and also invite your friends so that it will be an aid in your preparation to GATE examination 2023. So far, we had been discussing previous year questions from GATE Metallurgical Engineering. This week also, we will be doing the same. We will discuss 3 to 4 questions, and at the end of the session, in case you feel any doubts, please do react. Also, send me an email in case you want an additional explanation session on any of the topics that we have discussed so far. So, on that note, let us move into today's questions. So, the first question that we'll be seeing today is the C by A ratio of zinc, which is an HCP crystal, is 1.856. Slip occurs at room temperature, and it's mentioned that slip at room temperature occurs most easily on which of the following slip systems in zinc? Note, in HCP metals, the ideal C by A ratio is 1.633. So it was asked in GATE Metallurgical Engineering 2018 for 1 mark. So here the thing is that the C by A ratio of a particular crystal is given. The crystal is in HCP, C by A ratio is given hence, and it's also mentioned that slip occurs at room temperature. Here and in the options we have been given a series of planes as well as directions, and the planes and directions together make up what is known as the slip system. So based on the conditions that is mentioned in the question, we have to decide which of the following slip systems is most favorable. And we should always keep in mind that slip occurs on those planes which are the most densely packed. So which of the following will be most densely packed under this condition? So, we know that the ratio of these lattice parameters play an important role in deciding the slip system that is active in a crystal. An HCP crystal, as you may recall, has a lattice parameter A and C, that is the vertical parameter, and the C by A ratio is as mentioned in the ideal case. We also know that the angle gamma between the lattice parameters A is 120 degree, the rest of the angles being 90 degree. So that is the basics of an HCP crystal. So moving on, you might remember that the number of slip systems in an HCP crystals is 3. So what are they? Basal, prismatic and pyramidal. Basal is the most common slip system in an HCP crystal, that is the usual slip system in an ideal case, and that's the slip system consists of the slip lane 0001 and the slip direction 112 bar 0, and it is commonly found as the slip system in many materials like cadmium, zinc, magnesium, titanium, beryllium, etc. So if you see the figure, this is the basal slip system, that is the most common one, meaning that this is the most densely packed plane in an HCP crystal. The less favored slip systems include prismatic and pyramidal. Prismatic one consisting of the plane 101 bar 0 and the direction 112 bar 0. It is usually found in materials like titanium, and the pyramidal one being the least favored slip system, it includes the slip lane of 101 bar 1 and the direction 112 bar 0. It is exhibited by materials like titanium and magnesium. So in this figure, this is the pyramidal slip system. So from this examples, you may know that titanium is capable of existing or of exhibiting all three slip systems. So there must be some factor that contributes to the change of a particular slip system that is favored. So these factor includes the C by A ratio as well as the temperature at which the slip is operating. So basal and most commonly and most closely packed plane in an HCP crystal, as I mentioned, is 0001, and they are usually active in all HCP materials like zinc, cadmium, etc. And I also mentioned that the prismatic and pyramidal planes are less favored. The prismatic plane is usually favored at higher temperatures. The ideal HCP configuration C by A ratio is 1.633, but since it's already mentioned it's ideal, it doesn't occur in any metal. The values are usually higher or lesser. So in zinc and cadmium, these values are higher. For zinc, it is 1.856, and for cadmium, it is 1.886. For many other materials like magnesium, titanium, beryllium, zirconium, mercury, etc., the C by A ratio is lower. So, whenever the C by A ratio is low, the 0001 plane is not the most densely packed plane. That is, it loses its distinction as the most densely packed plane, hence, it won't be favored. Therefore, whenever the C by A ratio is smaller than the ideal value, 0001 plane will not be the most densely packed one, hence, they will not be favored. That is the reason why materials like titanium show additional slip planes, or in magnesium, the 1011 plane deforms above a particular temperature. So, keeping these points in mind, let us come back to our question. The C by A ratio of zinc, which is NCP material, is 1.856, which is greater than the ideal value. Also, it is mentioned that the process is taking place at room temperature. Therefore, we can say that the most common basal plane will be the active slip system in our case also. That is the 0001 112 bar 0. At it, so if it was at a higher temperature, it would have been prismatic. If the C by A ratio was lower than ideal, it would have been a pyramidal on another plane. It would not be the basal plane. But since the conditions are pertaining that of the ideal one, the most densely packed plane will be the basal plane, and hence our option will be 0001 plane with 112 bar 0 direction. So I hope it's clear to all of you. So that is the case. So the salient features of this particular question is that the C by A ratio, whenever it is greater, basal plane will be the active one. At room temperature, plane will be active. At higher temperature, prismatic will be active. When C by A ratio is lower, our basal plane won't be active. So that is the case. I hope it's clear to all of you. Now we can move on to the next question. Match the four tensile stress strain curves P, Q, R, and S with the materials listed in the box. It was asked in GATE Metallurgical Engineering for 2 marks. It's a very simple and direct question. So here we have four lines in the stress strain curve with the different characteristic features. And in our options, four materials are given to us: polyester PET, that is a polymeric material; high purity copper, a metallic material with a high ductility; mild steel, again a metallic material; then finally a brittle material or soda lime glass, characteristic to that of ceramics, etc. So, based on the features in this graph, we have to match these graphs to these particular materials. So, the basic stress strain diagram for different materials are shown here. Let us start with the brittle material. In the brittle material, there is no elastic or plastic deformation taking place. The proportional limit, elastic limit, yield point, ultimate tensile strength will all be the same, and for a limited value of the strain, the material will break. Also, the area under the curve, that is the maximum amount of energy that the material can absorb before fracture, will also be very less. So, materials like ceramics, wood, glass, cast iron, PMMA, etc., are examples of brittle materials that exhibit such kind of a stress strain curve. So the next is ductile materials. Ductile materials, if you see, have a characteristic curve like this. The amount of stress required will be high and it undergoes a large amount of strain as well. So it will exhibit both elastic as well as plastic deformation. It will have an yield point. It will also have an ultimate tensile strength point, and finally a fracture point. So what is the proportional limit? Proportional limit is the point up to which stress will be proportional to strain. Again, we have something known as an elastic limit, meaning that stress won't be proportional to strain, but up to that point, if we release the load, the material will be able to regain its initial configuration. Then we will reach something known as an yield point, after which the material exhibits only plastic deformation. And there is the ultimate tensile strength, which gives us the maximum value of the load the material can take before fracture. Finally, we have a fracture point. And in metallic materials, it's also important to know that materials like mild steel will exhibit something known as an yield point phenomena. That is, in this elongated curve, there will be a dip in the stress at one particular region after the yield point. So, what does this yield point phenomena indicate? So, the yield point phenomena means that the material will be having very small atoms as impurities like carbon and nitrogen. And due to the presence of these carbon and nitrogen atoms, the dislocations will be pinned at these points, leading to the formation of what is known as quartal atmosphere. And due to the quartal atmosphere, the dislocations will be pinned at that point, and after reaching a certain value of stress, the dislocations will be set free. And a large amount of strain will take place at a lower value of stress, that is the dip in the value of stress. So this is the yield point phenomena in materials like mild steel. Again, it will plastically deform up to the ultimate tensile strength and then break at the fracture point. So this yield point phenomena is characterized by an upper yield point and a lower yield point. So it's usually exhibited by materials having small atom impurities that are capable of pinning the dislocations and hence increasing the stress required to propagate the dislocation. Then finally we have plastic materials. Plastic materials also exhibit a large amount of elongation or strain, maybe 100 to 300 times in certain cases. But the amount of stress that is required to produce such an amount of strain will be comparatively very less when we are seeing with respect to that of a ductile material. So these are the basic features in different materials when we are comparing their stress strain diagram. So going back to our question, we will see the first option P. Here we can say that initially there is a proportional limit is there, then we can see a characteristic dip in the curve. So this is the upper yield point, lower yield point, and this is the region in which there is an elongation or strain happening at a lower value of stress. That is, at this point, the dislocations were pinned by the carbon and nitrogen, then the dislocations were set free due to the increased amount of stress at this point, and that at a lower stress value deformation happened, and again plastic deformation happened until ultimate tensile strength and eventually fracture occurred. So this is the characteristic stress strain diagram for mild steel. So next again we have a material with a similar amount of stress and elongation, but it does not exhibit any yield point phenomenon. Therefore we can say this is high purity copper. So the third red curve that we have is the amount of stress required is comparatively very less. It fractures very fast. The area under the curve is also very less. Therefore, it is somewhat of a brittle material. And from our options, we can say that it is soda lime glass. And finally, we have the green curve in which a large amount of strain is taking place, but at a relatively very low value for stress. That is the case of a polymeric material, that is polyester in our option. So P will be 3, that is mild steel. Q will be 2, high purity copper. R will be soda lime glass or 4. And finally S will be polyester. So based on these comparisons, we can say that the solution to this question is option C. I hope it's clear to all of you. So I hoping that it's clear to all of you. I'm moving on to the next question. The next question is the sequence of precipitation to reach stable equilibrium during the aging of aluminium 45 weight % copper alloy is. It was asked in GATE Metallurgical Engineering 2017 for 1 mark. So in this particular question, it may be that you might already be knowing the sequence of precipitation, but it's nonetheless important that we understand precipitation hardening in aluminum alloys. So this is an aluminum alloy with 45 weight % copper, and precipitation hardening is taking place, and during the precipitation hardening a series of precipitates are formed before forming the final CuAl2 precipitate. So what is this? What is the sequence in which this is happening? So initially we have the phase diagram for an aluminum copper alloy. So first we have what is known as solution treatment or solutionizing. During the solution treatment, the alloy will be heated to a temperature above the Solvus line. This is the Solvus line. It is heated to a temperature above the Solvus temperature and kept it or soaked in that particular temperature for a sufficient amount of time so that homogeneous alpha phase will be produced. Here all the precipitates of CuAl2 will be completely dissolved and only alpha will be there, and that is the point M. From this point M, we will quench the alloy rapidly to a point F such that we will get a supersaturated solution of copper. That is, the solution will be having excess copper, and the atoms will not have sufficient time to diffuse to their potential nucleation type so at a site, so that the copper Al2 precipitates can form. And the next step is the aging process, where the supersaturated alpha is heated below the solvent's temperature to produce finely dispersed precipitates. That is, once quenching it to point F, then this particular solution is slowly heated until below the solvents so as to get the precipitates. The precipitate is our CuAl2 precipitate. Since the supersaturated alpha in this region is not stable, the extra copper atoms that is present will diffuse to numerous nucleation sites and then will grow. So this is how first GP zones or Guinear-Preston zones are produced. Upon quenching from the solid solution, the copper and then heating, the copper atoms will start coming together. They will homogeneously nucleate to form Guinear-Preston zones. These Guinear-Preston zones are disc-like. They are formed as part of the FCC lattice itself. Therefore, they are completely coherent with the lattice. The formation of a finely dispersed precipitate is our final objective, but before forming the finely dispersed precipitate, initially GP zones are produced. Therefore, all options have GP zones. So first GP zone will be produced. Then what happens? Some of these GP zones or disc-like precipitates will start growing more and more three-dimensionally and consume more copper atoms. Therefore, the number of GP zones will reduce and a new state of the precipitate or the theta double prime precipitate will be formed. They are capable of catching the migrant copper atoms more efficiently than the initial GP zones. That is the theta double prime precipitate. After the theta double prime precipitate is formed, heterogeneous nucleation starts taking place and competes with this homogeneous nucleation. And the heterogeneous nucleation will take place at defect locations, usually dislocations. And these are also coherent precipitates. Coherent precipitate meaning that both GP, theta double prime, and theta prime are formed as part of the FCC lattice itself. They're completely coherent, and therefore hardening won't be to of that extent. And also it is important to remember that from GP to theta prime and from theta double prime and from theta double prime to theta prime, three-dimensional nature of the precipitate goes on increasing. And finally, as time goes on, what will happen? The final CuAl2 or theta precipitate will nucleate at grain boundaries. These precipitates are fully three-dimensional, but they are incoherent. Therefore, they will lead to increase in hardness. That is, they won't match with the FCC lattice of the aluminum copper alloy, and they are incoherent. And if we are examining the yield strength or hardness versus the logarithm of aging graph, that is, we will be able to see that initially GP zones are produced, then theta double prime is produced, theta prime is produced, and theta is produced. Here it is coherent, 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 coherent. Again, once it starts going to here, it becomes more and more incoherent. And maximum hardening or yield strength of the alloy will be obtained between theta double prime and theta prime. Therefore, we can say in this particular question, the sequence of precipitation will be GP zone, theta double prime, and theta. So we may be thinking that this sequence of precipitation is very easily rememberable, but we should know what of among these are coherent, what among these are incoherent. So incoherent will be theta alone. Theta prime, theta double prime, and GP zone will be coherent. Incoherent one will be the last precipitate. And what are the temperatures associated with age hardening? Initially, we will be heating above the solvents. We will homogenize it at that so that we get alpha only. Then we will rapidly quench to F so that we will be having a supersaturated solution of copper. From there, we will slowly heat till below N so that we will get our CuAl2 precipitate. This is the process of age hardening in aluminum copper alloy. So our answer is GP zone, theta double prime, theta prime, and theta. So that is the question. Sorry, answer to this particular question. It was asked in GATE Metallurgical Engineering 17 for 1 mark. So I hope it's clear for all of you. And then we will move on to our final question. In polymers such as epoxies, creep resistance can be enhanced by dash. It was asked in GATE Metallurgical Engineering 15 for 1 mark. So here we will be discussing creep. We know creep in steel and other ferrous materials, etc., or non-ferrous metals, but we never discuss creep when they are pertaining to polymers. So in case of polymers, creep can be said as the tendency of the polymeric material to distort under the applied load, same as in case of metals and all, at an increased temperature. But in case of a polymer, what happens? The polymer chain will start uncoiling and they will begin to slip past one another when a constant stress is applied at higher temperature. This phenomenon is completely temperature dependent, since at increased temperature, what will happen? There will be a decrease in the secondary bonding, and also due to increased chain vibration, there will be increased chain mobility. Now that we have understood what is meant by creep in polymers, it is necessary to see what increases the creep resistance of polymers. So there can be distinction between crystalline and amorphous polymers. Sorry. There can be distinction between thermoplast and thermoset polymers and so on. So first we will see between crystalline and amorphous polymers. Crystalline polymers, since they have a high degree of secondary bonding, have greater creep resistance than amorphous polymers. Then between thermosets and thermoplast. So creep resistance of thermoset polymers are inherently greater when comparison to thermoplast polymers, and creep resistance in such materials can be increased by increasing the cross-linking, because by increasing the cross-linking between the secondary chains, what will happen? Glass transition temperature will increase. Also at the same time, with increase in cross-linking, there will be a resistance to the sliding and uncoiling of the chains under the applied load, and hence this raises the creep softening temperature. Therefore, thermoset polymers like epoxy in our example should be fully cured so that their cross-linking density is maximum. And the creep resistance of thermoset polymers can also be increased by increasing their molecular weight. So that is the case of thermoset polymers. Now we have thermoplast polymers. Thermoplast polymers are weaker in comparison to thermoset for creep resistance. The creep resistance can be increased by controlling the arrangement of the side groups or the network structure of the chain. Crystalline and semi-crystalline polymers are more creep resistant than amorphous polymers due to their more three-dimensional network structure. Also, polymers with large pendant groups or side groups will ensure more chain and entanglement. More chain entanglement means it will be difficult to uncoil them, and therefore there will be having a higher degree of creep resistance. So therefore we can say that cross-linking and backbone stiffness will contribute to creep resistance. So whatever we have to keep in mind, we need to increase the glass transition temperature, size of the pendant group, then increasing the cross-linking in case of thermoset polymers, then increasing the backbone stiffness, etc. These are the some of the ways in which polymer creep resistance can be improved. So in our case, our polymer is epoxy. It is a thermoset polymer, and by increasing the cross-link density, glass transition will increase. At the same time, untangling will increase, softening temperature will increase, and therefore creep resistance can be improved. Therefore, our answer is option B. So I hope it's clear to all of you. So thank you for your kind attention, for spending time with me on these four questions. I hope the concepts are clear to all of you. In case you feel any difficulty for these concepts that we have discussed so far, please feel free to email me at santra.pmrfiatm@gmail.com. Please do see the sessions on Thursday from 6 p.m. to 7 p.m. I encourage all those who are appearing for GATE 2023 to see these sessions so that you will get a better approach on how to solve these questions during the examination. So that is all for this week. Thank you so much for spending your time. Hoping to see you next week. Thank you. Have a great week and bye bye.